Have you ever set down a hot cup of tea and watched it slowly lose its warmth? Or noticed how an ice cube melts in your hand without you doing a thing? These simple observations are not just coincidences, they're everyday glimpses into thermodynamics, the science that explains how energy moves and transforms. Today, we'll uncover the very first building blocks of this subject, the thermodynamic terms. Whether you're learning this for the first time or revisiting to strengthen your understanding, stay with me. You're about to see how these concepts are the keys to understanding everything from engines to your morning tea. Let's start with the basics. What exactly is a system? In thermodynamics, the system is simply the part of the universe you choose to focus on. Everything else, literally the rest of the universe, becomes the surroundings. Imagine you're mixing two chemicals in a beaker. The beaker and the reaction mixture? That's your system. The air around the beaker, the lab table, even your hands? All of that is the surroundings. There's a simple equation you can remember. Universe is equal to system plus surroundings. Now, to separate them, we draw a boundary. This could be a real wall, like the glass of the beaker, or an imaginary line we create to define what we are observing. Take a moment, picture any process, water boiling, fuel burning, even your body generating heat. Every process can be divided into a system and surroundings. It's as simple and as powerful as that. Quick insight is never use HNO3 or conc. H2SO4, they oxidize hydrogen instead of liberating it. Here's something important, not all systems behave the same way. Depending on what crosses the boundary, we categorize systems into three types. Open system, both energy and matter can flow in and out. Picture an open pot of soup simmering on the stove. Heat escapes and steam carries matter away. Closed system, matter stays put, but energy can pass through. Think of a tightly sealed bottle of water warming up in sunlight. No water leaves, but heat still gets in. Isolated system, neither energy nor matter crosses the boundary. This is like a perfectly insulated thermos flask. In reality, perfect isolation is almost impossible, but thermos flasks come close. Pause for a moment. Can you imagine which systems are around you right now? Look around and see which examples you can spot. The quick insight is hydrogen diffuses faster than any gas due to its low molar mass. To describe a system fully, we need to specify its state, in other words, its measurable properties. These include pressure, written as P, volume, written as V, temperature, written as T, and the amount of substance, often noted as N. We call these state functions because they depend only on the current condition of the system, not on the path taken to reach it. For example, if a gas occupies 2 liters at 1 atmosphere of pressure, it doesn't matter whether you compressed it or heated it to get there. The state is defined simply by those values, 2 liters and 1 atmosphere. Try thinking of it this way. State functions are like the location pin on a map. It tells you exactly where you are, regardless of how you arrived. The quick insight is reaction with chlorine in sunlight is explosive, handled with caution. One of the most essential state functions is internal energy, symbolized by the letter U. Internal energy is the total of all energies stored in a system, chemical, kinetic, potential, everything. This energy can change in 3 ways: 1 when heat enters or leaves the system, 2 when work is done on or by the system, 3 when matter crosses the boundary. We describe this change using the formula U is equal to Q plus W. Let's spell that out carefully. Delta U equals Q, the heat exchanged, plus W, the work done. Here's a quick example to make it real. Suppose you add 500 joules of heat to a system and it does 200 joules of work on the surroundings. Remember, work done by the system is negative. So, Q is equal to plus 500 joules, W is equal to 200 joules. Then, U is equal to 500 plus 200 equals plus 300 joules. This means the internal energy increased by 300 joules. Every time you calculate U, you're simply tallying up the energy coming in and going out. The quick insight is always convert grams to moles before using molar volume at STP. So, why does this matter? Because thermodynamic terms are the language we use to understand why your tea cools down, how an engine powers a car, or how a battery stores energy. Every process in chemistry and in life can be studied by defining the system, the surroundings, the boundaries, and the flow of energy. Remember this equation, U is equal to Q plus W, because it's the foundation you'll build on in every thermodynamics lesson ahead. Stay curious and join me in the next video where we'll explore work, enthalpy, and heat capacity and see how energy transforms in ways you can calculate and predict. The quick insight is hydrogen's role as clean energy fuel positions it as fuel of the future. Now, before we close, let's pause and think about safety. Hydrogen, though colorless and light, is highly inflammable. Even a small leak can form an explosive mixture with air if the concentration is anywhere between 4 to 74%. That's why in laboratories and industries, hydrogen is always stored in strong steel cylinders fitted with safety valves. How do we actually confirm if the gas we've collected is hydrogen? There's a simple classic test. Bring a burning splint near the mouth of the test tube, and if you hear a sharp pop sound, that's unmistakable evidence of hydrogen gas. But beyond the laboratory, the study of hydrogen carries deeper meaning. It helps us understand how energy transforms in engines, in rockets, and even in the cells of living organisms. So, remember, treat hydrogen with respect, use it safely, and appreciate its significance as one of chemistry's most important elements.